Okay friends, if you recall the last class, we have seen mainly two important parts in linear algebra. First of all, we have seen what is the meaning of linearly independent set and linearly dependent. So, I believe that you are in a position to recall the difference between linearly dependent and linearly independent set of vectors. After that, we have seen what is the meaning of dimension of a vector space. If you recall, then dimension of a vector space is simply the number of elements in the basis of a vector space. And then what is the meaning of basis of a vector space? Basis of a vector space means a set is said to be a basis of the vector space if it satisfies two important properties. First one is that the given set must be linearly independent, and second is that the given set must span the whole space, whole vector space V. So, S is a basis for a vector space V if and only if S is linearly independent and S spans V, that is span of S must be equal to V. Now, suppose that V is a finite dimensional vector space. V is a finite dimensional vector space. Okay. Means what? The dimension of the vector space is finite. Dimension of vector space is finite means number of elements in the basis of the vector space is finite. Okay. So, first very important result is that dimension is unique, but basis is not unique. What is the meaning of this? Look at here, dimension is unique, basis is not unique, means what? Number of elements in the basis is unique, but the basis is not unique. For a vector space, you can have infinite number of bases, but the number of element in each basis for a special vector space cannot be different, it must be same. For example, suppose you are talking about R3. We are talking about R3. Okay, dimension of R3 over R is 3. Dimension of R3 over R is 3. It means what? Number of elements in the basis must be 3 only. So, suppose S1, suppose I am calling here S1 is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is a basis of, this is called a standard basis for R3. It is a standard basis, natural basis for the vector space R3. But you can see that if there is any other set S2 which may also be a basis for R3. Suppose for example, I am taking here 1, 0, 0, 1, minus 1, 0, 0, 0, suppose 1 I am taking. So, if S2 it is also basis, then look at the set S1 and S2, both are different. Both are different, but if when S1 is a basis and S2 is a basis, number of elements in S1 and S2 cannot be different. If S1 has 3 elements, S2 has, if S1 and S2 both are basis for R3, the number of elements in S1 must be equal to the number of elements in S2. Okay, so it means that number, if V is a finite dimensional vector space, then any two bases of the vector space V will have the same number of elements. Number of elements in the basis cannot be different. Second property is also very important. If you look at the slide also, that second property is that if V is a vector space, V is a vector space and dimension of V is a vector space, dimension of n, V is equal to n, it is finite. Dimension of V it is n and it is finite. Okay. Then it tells us that any set which consists of more than n vector is linearly dependent. Any set which consists of more than n vectors is linearly dependent. What is the meaning? Again you take for example R2, I am taking at this stage R2 is a vector space. R2 it is a vector space, and I am calling here S is the set of all elements of the type 1 0 0 1 1 2. Look at here, 1 0 it is an element of R2, 0 1 it is an element of R2, 1 2 it is an element of R2. So S it is a subset of R3, so R2, S it is a subset of R2. Then whether S is linearly dependent or independent, there is no need of anything checking. Look at here, the moment dimension of V is equal to n and n is finite, dimension of R2 is 2 and 2 is finite. Therefore, any set which consists of more than the dimension of the vector space, more than n elements, where n is the dimension of V, then S is linearly dependent. So here the set S consists of 3 elements, and dimension of R2 is 2, dimension of R2 is 2, and here S contains 3 elements, therefore S is linearly dependent. Okay. So this result is also equally important. If dimension of a vector space is finite and it is known, and if you see the given set, if you want to check whether it is linearly dependent or no, if the number of elements exceeds the dimension of the vector space, it will imply that the given set is linearly dependent. Take for example again R3. Now I am taking here R3. In R3, dimension of R3 is 3, and take the set S as consisting of the elements 1 minus 1 1 0 1 1 1 2 3 2 1 0, and I am putting here one more element 0 0 1. See this set, the set S. How many elements are there? This is one element, 1 2 3 4 5. There are 5 elements, and S is a subset of R3, and dimension of R3 is 3, and it consists more than 3 vectors. Therefore, the set S is linearly dependent. Therefore, this implies that S is linearly dependent. So I believe that you are in a position to decide this criteria. If the number of elements in the set exceeds the dimension of the vector space, then the given set S is linearly dependent. If you look at one more result, third, that suppose dimension of V is a vector space, it is n and it is finite, and if S contains n vectors u1, u2, u3, un, and if S is linearly dependent, S is linearly independent. Dimension of V is n and n is finite, S contains n vectors and the set S is linearly independent, it will imply that S is a basis. This will imply that S is a basis. S is a basis for V, for the vector space V. So if you see, if you want to show that the given set S is a basis or it is not a basis, then you are supposed to check two things. First is that the given set must be linearly independent, and the given set must span the whole vector space V. But the moment if you prove that S is linearly independent and see what is the dimension of the vector space and number of elements in the given set S is equal to the dimension of the vector space, then there is no need of checking the second property, that is spanning property. Just you check that S is linearly independent, that will imply that S is a basis. Second property follows from the fact that number of elements in the given set S is equal to the number of is equal to the dimension of the vector space, that will imply that span of S is equal to V, and hence S is a basis for V. Therefore, this we shall see some examples based on this also. And one more result, see what is the meaning of dimension of W1 plus W2. If you look at the fourth important properties, that suppose now W and W2 are finite dimensional of a vector space V, then dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. This is very useful result. The dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Now, I am going to use the previous result. Suppose the given set S is here. S is the set consisting of 3 vectors x square plus x, x minus 1 and x plus 1. Then so that S is a basis for P2. What is P2? This P2 is the set of all polynomials of degree less than equal to 2. Do you recall the last class? What is the dimension of Rn over R is n, but dimension of Pn over the field of real number is n plus 1. Okay. And therefore, if P, what is dimension of P2 now? Dimension of P2 is 2 plus 1, that is 3. And here the set S consists of 3 vectors x square plus x, x minus 1 and x plus 1. So therefore, how to decide that S is a basis for P2 or no? So see here, number of elements in the given set S is equal to the dimension of P2. Therefore, we shall check only one property, whether S is linearly independent or it is not linearly independent. The moment S is linearly independent, it will imply that S is a basis for P2. We shall not check the second property, that S spans P2. The reason is that number of elements in the given set S is equal to the dimension of the vector space. So therefore, we are going to check that the given set S is linearly independent only. Now again recall the last class, how to check the given set is linearly independent. Make a linear combination, set it equal to 0, see what are the solutions. If you are getting only 0 solution, no any other solution except the 0 solution, the given set will be linearly independent. If there is any other solution which is different from 0, the given set will be linearly dependent. So look at here, alpha, beta, gamma, these are scalars such that alpha into x square plus 1 plus beta into x minus 1 plus gamma into x plus 1 is equal to 0. That we are making a linear combination. This 0 is the 0 polynomial, remember here, this 0 is not the real number, 0 is a 0 polynomial. Okay. So rearrange, the coefficient of x square is alpha, coefficient of x is alpha plus beta plus gamma, and coefficient of the constant term in fact minus beta plus gamma. This is equal to 0. Now what is the meaning of a 0 polynomial? 0 polynomial means coefficient of each power of x must be equal to 0. Therefore, alpha into x square, so coefficient of x square must be equal to 0. So therefore, this alpha must be equal to 0. Therefore, similarly here alpha plus beta plus gamma must be equal to 0, minus beta plus gamma must be equal to 0, because it is a 0 polynomial. Fine. And therefore, if you see that if alpha, from here this alpha is 0, alpha plus beta plus gamma is 0 and minus beta plus gamma is 0. Solve, see what is either whether alpha plus alpha, beta, gamma all are 0 or either any non-zero solution. Okay, so from this equation we are going to get that alpha is 0, alpha plus beta plus gamma is 0 and minus beta plus gamma is 0. So when alpha is 0, then from second we will get beta plus gamma is 0 and from here we will get minus beta plus gamma is 0. See that beta plus gamma 0 minus beta plus gamma 0, from here we are getting that beta is also 0 and gamma is also 0. Therefore, alpha is 0, beta is 0 and gamma is 0. This is the only solution, there is no any other solution. So alpha, beta and gamma all coefficients are 0. Therefore, what is the conclusion? From here we only conclude that S is linearly independent. If you look at the second property, dimension of P2 is 3 and that is equal to number of elements, therefore S is a basis for P2. Clear this part, S is a basis for P2. Let us see another example. Look at here again, this set S, it is a subset of R3. This set, it consists of 3 elements again, 1 2 1, minus 1 1 0 and 5 minus 1 2. Okay. And we want to again check whether this is a basis for R3 or it is not a basis for R3. Again recall here, if we can show that S is linearly independent, it will imply that S is a basis. Reason must be clear why. Because again here the number of elements in the given set S is 3 and this is equal to dimension of R3, and therefore S spans R3, and therefore if we can show that this set S is linearly independent, it will imply that S is a basis. Therefore, how to check that S is linearly independent? Again we shall make one linear combination, that is alpha 1 into the given element 1 to 1 plus alpha 2 into second element plus alpha 3 into third element is equal to 0, and this 0 is the 0 element of R3. And from here if you see that you are going to get 3 equations, 3 unknowns. What we are going to get here? From alpha 1 minus alpha 2 plus 5 alpha 3 is equal to 0 from here. Second element is here 2 alpha 1 plus alpha 2 minus 5, not minus alpha 3 is equal to 0. This is second one. Third is that alpha 1 plus alpha 2 into 0 plus alpha 3 into 0. Here there is little correction, this is 5 minus 1 and this is 2 in fact. This 0 is not, this is 2. So remember here this is 5 minus 1 2. Third element is 5 minus 1 2. So this is 5 minus 1 2. So from here you are going to get that alpha 1 plus 2 alpha 3 is equal to 0. Okay. So make a linear combination that alpha 1 into U1 plus alpha 2 into U2 plus alpha 3 into U3 is equal to 0, that is the 0 element of R3, and from here we are getting 3 equations, 3 unknowns, and therefore solve this equation and see what you are going to get. Of course since it is a linear and homogeneous, 0 0 0 it is always a solution. We will have to check is there any solution which is different from 0. If yes, it is linearly dependent. If no means there is no any other solution except the 0 solution, then the set S will be linearly independent. So let us see how to solve these 3 equations, 3 unknowns. Now recall our first 2 lectures where we have seen how to solve a linear system of equations. Here we are having homogeneous equation, 3 equations, 3 unknowns. Therefore we shall make, with the help of row echelon form or row reduced echelon form you can use, and from here you see that what is the solution. Alpha 1 plus 2 alpha 3, either use your row reduced echelon technique or use your class 10th technique. Alpha 1 plus 2 alpha 3 is 0. So you can substitute here the value of alpha 1 equals minus 2 alpha 2 in the second equation as well as in the first equation also. Then you will get an equation in alpha 2 and alpha 3. Solve this one, 2 equations, 2 unknowns. They see that alpha 2 is 0 and alpha 3 is 0. Therefore when alpha 3 is 0, then from here you will get alpha 1 is also 0. So this one, or you use the row echelon form technique first of all. That will be the most convenient technique. So, and what is row echelon form technique or row reduced echelon form technique, that I have discussed in the first 2 lectures, and here you see that what is the solution of this homogeneous system of equation. You will find that you will not get any other solution except the 0 solution. So solving this one, you will get that alpha 1 is 0, alpha 2 is 0 and alpha 3 is 0. Therefore S is linearly independent. As I have discussed, or I have told you, that we shall not check that S spans V. It follows from this fact, step 2, that dimension of R3 is 3 and that is equal to the number of elements in S. Therefore S spans R3 and hence S is a basis of R3. That is the final conclusion. This example I am leaving for you as an exercise. See on the slide, everything explained nicely. First of all, S is the subset of R3, which satisfies certain restriction that x1 plus x2 plus x3 is equal to 0. It will simply, this is an equation of a plane passing through origin, x1 plus x2 plus x3 is equal to 0. This is an equation of a plane passing through origin. Okay. So, question is find a basis for the given set S, that is for the given plane and find the dimension of this plane. Okay. You can see easily that first of all S is a subspace, although it is given here, but you can prove that S is a subspace of R3. And from here you see that this S is in fact the span of this one. This one, all these things I am leaving in an exercise for you, see details how it is coming. And you can see that dimension of S is 2, and in fact this set B, the set B which is written here, this set B is a basis, this set B is a basis for the set S, and number of elements in B is 2, therefore dimension of S is 2. So, for detail I am leaving in exercise, everything is explained nicely on this slide. Now, I shall start a different topic, what is called linear transformation. Linear transformation. Here we will have two vector spaces and a mapping. Two vector spaces, but over the same field. What is the meaning? That U and V both are vector spaces over the same field F. Means if U is a real vector space, V must be a real vector space. If U is a complex vector space, V must be a complex vector space. One real, other complex you cannot take. That is the meaning that U and V both are vector spaces over the same field. Although in this course we are taking only real vector space, therefore U and V both are real vector spaces. Then a mapping T from U to V is called a linear transformation if and only if T satisfies two properties. First one is that T of U plus V must be equal to TU plus TV for all U and V from the domain set U, and T of alpha U must be equal to alpha times TU, where alpha is any real number. If these two properties are satisfied, we shall say that T is a linear transformation. So, T is a linear transformation from a vector space U to another vector space V if and only if T of U plus V is equal to TU plus TV for all UV coming from U, and T of alpha U is equal to alpha into TU for all U coming from U and for all real alpha. Let us see one example. Suppose U is a real vector space, then define an identity transformation or identity map from U to U itself by the relation that I of U is equal to U for all U from U. Therefore, what is I of U plus V? I of U plus V is U plus V, and U is in fact I of U because I is identity transformation and V is also I of V, and therefore I of U plus V is I of U plus I of V, and I of alpha U if you see I of alpha U is equal to alpha U because I is identity transformation, and again U is, if U is, look at here, if U is I U, therefore I is the identity transformation, I is a linear transformation. Similarly, you can check that zero transformation is also a linear transformation. Zero transformation is linear transformation. See one more example. Reflection about x-axis. You can check that T of xy is equal to x minus y. Again, it is a linear transformation. Just you take that. Suppose U you take is x1 y1 and U2 is x2 y2. See what is U1 plus U2. Then you see what is T of U1 plus U2. You will see that is T of U1 plus T of U2, and T of alpha U1 is alpha times T of U1, that will imply that T is a linear transformation. So, reflection about x axis which is defined in this fashion, that T of x y is equal to x minus y, it is a linear transformation, it will satisfy both the properties. Check this part very clearly, that it will satisfy T of u1 plus ut is T of u1 plus T of u2, and T of alpha u is alpha times T of u. See these two very important result, that if T from u to v, it is a linear map or linear transformation, T from u to v it is given to be a linear transformation, then T of 0 must be equal to 0. But remember here I am writing a T of 0 u. 0 u, what is the meaning of 0 u and 0 v? 0 lower suffix u and 0 lower suffix v, 0 u. 0 u means it is the 0 element of the vector space u, 0 v means it is the 0 element of the vector space v. So both are 0, but both 0 are different, one is coming from the set u and other is coming from the set v, that is the basic difference. And T of minus u is equal to minus of T u for all u in u. These are two very basic properties of a linear transformation. So the moment T of 0 is not equal to 0, it will imply that T is not a linear transformation. So if you want to check, if you want to decide that if T is not a linear transformation, check whether T of 0 is equal to 0 or no. If it is not, if T of 0 u is not equal to 0 of v, then it will imply that T is not a linear transformation. But if T of 0 u is equal to 0 v, does not mean at all that T is a linear transformation. We will have to show some other properties, that T of u plus v is equal to T u plus T v, and T of alpha is equal to alpha times T u. And just you see that T of k is equal to k T u, and therefore from this property it follows, just you take k is equal to 0, you will see that first property follow, T of 0 is equal to 0. If you take k is equal to minus 1, if you take k is equal to minus 1, then it will imply that T of minus is equal to minus T u. So these are two very important properties. Let us see two important definitions. What is the meaning of range space of a linear transformation, and what is null space of a linear transformation? First of all, u and v both are vector spaces we are taking over the same field f, or they are the real vector spaces, and T from u to v is given to be a linear transformation. Okay. Then range space of T, it is the set of all points coming from this set V. So once more, see what is the meaning of range space of a linear transformation and null space of a linear transformation. Range space of T, T is a linear transformation from u to v, then range of T, first of all it will be a subset of v, not u. So range of T, it is the set of all elements coming from v, such that T of u is equal to v for some u coming from u, and this set is called range space of T. It is the set of all elements of the type T of u, where u is coming from the domain set u. And null space of T, it is a subset of the domain space u. Remember here, range space of T, RT, it is a subset of V, but NT, null space of T, it is a subset of U. It is the set of all elements of the domain space U, such that T of U is equal to 0 of V. Means what? Null space of T, it is the collection of all those elements of the domain space U which are mapped on the 0 element of V, and this is called null space of T. There is another name for null space. If you see some other book, they are also calling it kernel of the linear transformation. Kernel of the linear transformation, that is being written here. Either kernel of a linear transformation or null space of a linear transformation, both are same. So remember these two definitions. Range space of T, it is a subset of V, null space of T, it is a subset of U with some specific properties. At this stage, I told you that range space of T, it is a subset of V, and null space of T, it is a subset of U, but more specifically, range space of T, it is a subspace of V, and null space of T, it is a subspace of U, more than subset. So, RT, it is a subspace of V, and null space of T or kernel of T, it is a subspace of the domain space U. So, these two results I have discussed, that range space of T, it is not only a subset of the vector space, it is a subspace of V, and null space of T, it is a null space of T, it is not only a subset of U, it is some little more, it is a subspace of U. Third is that this linear transformation T is 1 1 if and only if null space of T is singleton 0. That is null space of T consists of only the 0 element of the domain space U. So, T is 1 1 if and only if null space of T or kernel of T consists of the single element, that single element is the 0 element of the domain space U. Let us see this example. Here T is a linear transformation from R2 to R3. Defined in this fashion, T of x1 x2 is x1 minus x2 and x2. So, T is a linear transformation from R2 to R3. Suppose you want to check whether T is 1 1 or T is not 1 1. So, I told you that T is 1 1 if and only if null space of T consists of the single element, that is the 0 element of the domain space U. So, find what is null space of T. So, null space of T, remember null space of T, it is the collection of all those elements of the domain space which are mapped by T on the 0 element of V, and what is V here? R3. So, null space of T, it is the set of all x1 x2 in R2 such that T of x, that is T of x1 x2 must be equal to 0. And T of x1 x2 it is given here, T of x1 x2, that is x1 minus x2 and x2, that is equal to 0 of V. 0 of V means V is R3, R3 means 0 of R3 is 0 0 0, and therefore x1 is 0, x1 minus x2 is 0 and x2 is 0. x1 is 0, x2 is 0, x1 minus x2 is 0, therefore x1 and x2 both are 0. Therefore, see that null space of T consists of only one element, that is the 0 element of R2, therefore T is 1 1. So, remember that if you want to prove that T is 1 1, just you find what is the null space of the linear transformation, and null space of linear transformation is the set of all x coming from the domain vector space U such that T of x will be equal to the 0 element of the range, that is V. Look at this definition. Again, U and V both are real vector spaces, and T from U to V is a linear transformation, and U is finite dimensional vector space. Dimension of U is finite. Then how to find rank of the linear transformation? We have seen in our first two lectures how to find rank of a matrix. Here we are going to see how to find rank of a linear transformation. Rank of, then we must know first of all what is rank of a linear transformation. Rank of a linear transformation is the dimension of RT. What is RT? Range space of T. So, dimension of range space of T is called rank of the linear transformation, and dimension of null space of T, it is called nullity of the linear transformation. So, rank of T is the dimension of the range space of T, and nullity of T is the dimension of the null space of T or dimension of the kernel of T. Remember here RT and NT both are subspaces. So, if you want to find rank of the linear transformation, find dimension of the range space of T. To find the dimension of the range space of T, find a basis for the range space of T and see what is the number of elements in that basis. That will give you the dimension of the range space, and that dimension of the range space will be the rank of the linear transformation. If you want to see what is nullity of the linear transformation, then you see first of find null space of the linear transformation, find its dimension of the linear null space of T. To find dimension of null space of T, again you find a basis for the null space of T. When you have decided a basis for null space of T, then you see what is the number of elements, and that number of element will give you the dimension of null space of T, and that dimension is called the nullity of the linear transformation. So remember here, once more I am repeating here, rank of a linear transformation is the dimension of range space of T, and nullity of linear transformation is the dimension of the null space of T. Fine. And this result, then what is the relation between rank of a linear transformation and nullity of a linear transformation? This is given by a rank nullity theorem. This is called rank nullity theorem. The dimension of the range space of T plus dimension of null space of T is equal to dimension of U. Remember here, U is the domain space, T is a linear transformation from U to V. So dimension of range space of T plus dimension of null space of T is equal to dimension of U, not dimension of V. It must be clear. T is a map from T, it is a map from U to V. So dimension of range space of T plus dimension of null space of T is equal to dimension of U, not the dimension of V. The moment it is clear. So this result you are supposed to recall, that dimension rank of linear transformation plus nullity of linear transformation is equal to dimension of U. Let us see a few remarks. These remarks are very important. First remark is that dimension of range space of T is always less than equal to dimension of U. Why? T is a linear transformation from U to V, and dimension of U is finite. When dimension of U is finite, therefore by rank nullity theorem, dimension of range space of T plus dimension of null space of T is equal to dimension of U. This result. And dimension is always a non-negative number. It is always bigger than equal to 0. Dimension, it is the number of elements in a basis. Therefore, it cannot be negative. It is always bigger than equal to 0. So dimension of RT plus dimension of null space of T is equal to dimension of U, and therefore sum of two non-negative quantity is equal to something. Therefore each quantity has to be less than equal to dimension of U. So dimension of RT must be less than equal to dimension of U. It cannot be larger than the dimension of U. So remember here, dimension of range space of T is always less than equal to dimension of U. But something more is also to be noted. What is RT? Range space of T, it is a subspace of V. When it is a subspace of V, it is also a subset of V. Therefore dimension of RT cannot be larger than the dimension of V, because RT it is a subset of V. RT this is RT, it is a subset of V, and therefore see, dimension of RT cannot be the larger than the dimension of V. Hence from second property, if you look at here, if T is a first one, what we have seen, dimension of range space of T cannot be larger than the dimension of U. Second property, dimension of range space of T cannot be the larger than the dimension of V also. Therefore what is the meaning of these two? Dimension of RT is always less than equal to two quantity. Therefore dimension of RT is less than equal to the minimum of these two quantity. Okay. So if T is a linear transformation from U to V and U is a finite dimensional, then dimension of range space of T is less than equal to U. Since RT it is a subspace of V, therefore dimension of RT it is also less than equal to dimension of V, and hence from here it follows that dimension of RT will be always less than equal to minimum of the dimension of U and dimension of V. See third remark, if T from U to V is a linear transformation and dimension of U is finite, then dimension of range space of T is equal to dimension of U if and only if T is 1, 1. we have seen that T is 1 1 if and only if null space of T is singleton 0. And but from rank nullity theorem you see that dimension of RT plus dimension of null space of T is equal to dimension of U. And if dimension of RT is equal to dimension of U, therefore dimension of null space of T has to be equal to 0. And when dimension of null space of T is 0, that will imply that null space of T consists of the single element 0 element of the vector space V, and therefore T is 1 1. This is 1 if and only if both way it is true. So dimension of RT is equal to dimension of U if and only if dimension of null space of T is equal to 0. It follows from this rank nullity theorem, and therefore if and only if null space of T consists of the single element, that is the 0 element of the vector space B, if and only if T is 1 1. So this remark is also equally important. See, fourth remark, if dimension of RT is less than dimension of U, then T is not 1 1. It follows from the previous remark. What is remark 3? Remark 3 that if dimension of RT is equal to dimension of U if and only if T is 1 1. Both way it is true. T is 1 1, then dimension of RT must be equal to dimension of U. Both reverse way it is also true. If dimension of RT is equal to dimension of U, then T is 1 1. Therefore, if T is not 1 1, then dimension of RT cannot be equal to dimension of U. Dimension of RT is not equal to dimension of U, but dimension of RT is always less than equal to dimension of U, but therefore this shows that dimension of RT is less than, strictly less than U if T is not 1 1. So therefore, if dimension of RT is less than dimension of U, then T is not 1 1. It follows just from previous one. And what is the meaning of T is onto? T is onto means range space of T is the whole space V. So T is onto if and only if range of T is equal to V, and range of T is equal to V if and only if dimension of range space of T is equal to dimension of V. And from sixth one, if you see that T is 1 1 and onto, T is 1 1 and onto, both combine remark 3 and remark 4. T is 1 1 if and only if dimension of U is equal to dimension of, see what is remark 3? T is 1 1, T is 1 1 if and only if dimension of RT is equal to dimension of U. And if you see the next remark, T is onto if and only if dimension of RT is equal to dimension of V. Combine these two. Therefore, T is 1 1 and onto if and only if dimension of range space of T is equal to dimension of U is equal to dimension of V. So therefore, T is 1 1 and onto if and only if dimension of range space of T is equal to dimension of U is equal to dimension of V. Let us see this example. Now here T, it is a linear transformation from R4 to P3, from R4 to P3, and defined in this fashion: T of x1, x2, x3, x4, because this is coming from R4 and it is output is going in P3, the set of all polynomials of degree less than equal to 3. Then find kernel of T or null space of T and the basis for a null space of T, find range space of T and the basis for range space of T, and see that rank nullity theorem holds. So see here, first of all let us find null space of T or kernel of T. Null space of T or kernel of T, it will be the set of all elements of R4, all elements of R4 which are mapped on the 0 element of P3. 0 element of P3 means 0 polynomial. So we are going to see these 3 questions one by one. So null space of T, just this is the first line, is the just definition of a null space of T, set of all points of the domain space R4 which are mapped on the 0 element of P3, that is the 0 polynomial. So T of x is 0. So T of x 0, what is the meaning of 0 polynomial here? It is a polynomial in T. So coefficient of each power of T must be equal to 0. So therefore x1 is 0, x1 is 0, x2 minus x3, this x2 minus x3 coefficient of T is 0, and x1 minus x3 the coefficient of TQ, it is also 0. Just from here x1 is 0, x1 is 0, therefore from this one you will see that x3 is 0, x1 is 0, therefore x3 is 0, and when x3 is 0, then from here it follows that x2 is also 0. So x1 is 0, x2 is 0, and x3 is 0, but there is no restriction on x4, there is no restriction in x4. x4 is any real number. Therefore, can you see what is this one? 0, 0, x4. This x4 you can take it out. So what will be here? 0, 0, 0, 1. x4 is any real number. So what is this set? This set is all scalar multiples of 0, 0, 0, 1. And what is the meaning? Scalar multiples of this element 0, 0, 0, 1. And that is the span of the set consisting of the element 0, 0, 0, 1. So null space of T, it is the span of this set. And therefore, what is basis of null space of T? This is basis of null space of T. Why it is basis of null space of T? First of all, look at here. From here, this set spans the whole space null space of T. From span of this set is equal to null space of T. And therefore, this set spans null space of T, and this is a non-zero element. Therefore, any set consisting of a single element which is different from 0 is always linearly independent. Therefore, this set is also linearly independent. Therefore, it is a basis for null space of T. If it is a basis for null space of T, how many elements it has? One element. Therefore, dimension of null space of T or dimension of kernel of T is 1. Let us see how to find range space of T. Remember here, range space of T, T is a linear transformation from R4 to P3. Therefore, range space of T will be a subspace of P3. So, range space of T will be the set of all elements of P3 such that T of x is equal to P for some x belonging to R4, and T of x is equal to P. So, see what is Tx is already defined. T of x is x1 plus x2 minus x3 into T plus x1 minus x3 into Tq. And what is this one? In fact, x1 is a real number, x2 minus x3 is also a real number, x1 minus x3 is also a real number. So, what is this set? Do you recall? This is 1 T and Tq, linear combination of 1 T and Tq. And what is the meaning of linear combination of 1 T and Tq? That is the span of the set consisting of these three elements 1, T and Tq. So, it is this set. Range space of T, it is the span of a set consisting of three elements 1, T and Tq, because this is the set of linear combinations of 1 T and Tq. Again 1 T and Tq, you can check that it is always linearly independent, because if you take here A into 1 plus B into T plus C into Tq is equal to 0, then A is 0, B is 0 and C is 0. Again, span of this set is equal to RT. It means what? This set consisting of the elements 1 T and Tq spans the whole space RT. Therefore, this set is a basis for RT, and number of elements in this basis for RT is 3. Therefore, dimension of range space of T, that is the rank of the linear transformation, is 3. Therefore, rank of linear transformation is 3. What you have seen here? Dimension of range space of T is 3 and dimension of null space is 1. What is sum? Sum is 3 plus 1, that is 4, and this must be equal to the dimension of U, that is the range, domain space, and that is, what is the domain space here? R4. Dimension of R4 over the field of real number is 4, and you see that dimension of range space of T plus dimension of null space of T is equal to the dimension of R4. This is L, this is in fact T. So, dimension of kernel of T or dimension of null space of T plus dimension of range space of T is equal to dimension of R4. I shall stop this class here. In the next class, we shall see what is eigenvalue and eigenvector of a matrix. Thank you.